Let's check out section 8.2, and we'll find the margin of error and sample size for proportions. So thinking of that example we just did in the previous section, let's see if we could find the margin of error, assuming like we never did the math and someone just gave us the results. So we're given this confidence interval for the true proportion of churchgoers, and we found that it was anywhere from 36.52% up to 49.42%. And we want to figure out the margin of error, assuming we don't have the math a page or two ago. So the way we can find the margin of error is we can use the interval. We know that p hat is in the middle, and we add a margin of error on the right side, and we subtract a margin of error on the left side, meaning our interval is 2 margin of errors wide. So what we can do is we can find that width of the interval. So margin of error, I'm just going to do MOE for short, but that stands for margin of error. It'll be the width of the interval, and we'll just cut it in half, divide by 2. And so the width of the interval is just finding how wide it is. So it's subtraction. It'll be the upper limit minus the lower limit, and we'll divide by 2. So in this case, it would be 49.42. You could also do this in decimal form as long as they're both in decimal form. So it'll be 49.42 minus 36.52. If you're doing this on your calculator, you'll subtract, hit enter, and then divide by 2 to make sure it divides by 2. So we get 6.54%, and this should match our plus or minus 0.0645 from before. And so that's how we could find it if we didn't do the math, like if we were just looking at like a publication with some data and we wanted to figure out how big that margin of error was. So let's say maybe this is too much. So what are the 2 things we can do to decrease margin of error? So we've been learning over and over that a larger sample or increasing the sample size will give us less error. The other option is to lower the confidence percent, which is the worst choice. So increasing sample size is the better choice. But if we lower from like 99 to 95, we would also get a smaller margin of error, but that's kind of like lowering our standards. So that's not the best version. So let's say we're the researcher, we've decided that 6% is too much error. So what can we do to decrease this error? And how much do we want to increase the sample size by? So that really depends on what our desired margin of error is. So let me give you a formula before we start solving that. We learned, again, last section that our margin of error was that plus or minus piece. If you do a little bit of algebra and solve for sample size, you get this. The issue is usually when we're solving for sample size, we have no clue what p hat is or q hat. So this trick is to guess. So I'm going to call it p guess. And then q guess would just be 1 minus p guess, just like q is always 1 minus p. So the trick is to guess the biggest value because we'd rather overestimate than underestimate. So the secret is p guess is usually 50%. And let me show you why. So if we do 50-50, we get 0.25. And then let's just guess a few other numbers. So this, to see that this is the largest. So this will be the largest possible sample because we'd rather overestimate than underestimate. If we underestimate, then our sample is too small and we get too much error. So the safe choice is to always just have a little bit too much. So I'll show you, like, let's say instead we did 40%, so Q would be 60. That's a little bit smaller than 0.25. I don't know, think of some other numbers, maybe 30%. So then Q is 70%, 1 minus P. And 0.21, we could try the other direction. What if P is, I don't know, try some number, 75. Then Q would be 25, 1 minus P. It's smaller than 0.25. So 50-50 gives us the largest possible number. It tends to overestimate, but it's conservative. It's better to have too much data and waste a little bit of money than to save money, not have enough data, and have too much error. So we're gonna use 50-50 for our p-guess. So this will usually be 0.5 times 0.5 times z over e squared. We almost always use 50% for our guesses. Again, it just overestimates, which is better. So let's solve one of these problems. So if we go back to that churchgoer problem, it was 99%, so that's relevant for our z-score. I think if we go back to the math we just did, our z-score was 2.576. If you don't remember, it was because we put 99 in the middle, and then each tail got 0.005. And we found 2.576 when we found the z-score. And we've decided that we only want 3% error, so 0.03. So we're trying to lower the error from 6.45 to only 3%. And we will use our p-guess of 50% just to be conservative. So it usually overestimates, but again, it's better to have a little bit extra data to be safe, and that'll guarantee that our error is less than 3%. If we go a little too small, then it actually might end up being more than 3%, so that's why 50% will be our safe guess. So our sample size will be 50, and then 1 minus 50 is just 50, so it'll be 0.5 times 0.5 for 50%, and then we have the z-score over the error squared. I'm just referencing that same formula. And then on the calculator, 0.5 or 0.50, whatever. Sometimes adding the 0 helps us remind ourselves that it's coming from 50%. And then make sure both the z-score and the error are in parentheses together, and then we'll square them. And we get about 1843.27. And this is a sample size, so 0.27 doesn't make sense. So we have to have full numbers of people. The trick for sample size, though, is it's not normal rounding rules. We're always going to round up, again, because we don't want to underestimate and then create too much error. So we're always going to round up, regardless, to the next whole number. So we need a sample size of 1844. So we always round up. It's not traditional rounding. And that's because if we want to make sure our sample size is large enough, even one person short could make our margin of error too big. So we always just go up to, it's kind of to play it safe, and 50-50 is also just playing it safe. So both of these are just to play it safe. They're conservative guesses. We might overestimate, but overestimating is better and getting a little bit less error rather than underestimating and having too much error. So we always round up to play it safe, and then 50% is like our safe guess.